All right, in the second half of chapter 4, we have to start off by looking at reducing systems of forces and moments into what's called a resultant force and couple moment. Essentially, any system of equivalent force and couple moment. Any system of forces and moments can be reduced or simplified to, or probably best way to think about it, replaced by a single force and a single couple moment. Essentially how this happens is because as any system of forces acts on an object, there's going to be forces pushing in any of the three directions, and there's going to be some net force which is going to act translationally on the object, and that would be the resultant force. There's also going to be some resultant moment. Again, all of the moments, all the tendencies to turn and twist in the on the object can be reduced to a single twisting moment in one direction or another. Okay, essentially what this does, again, we have a single force. We call this a couple moment because it behaves like a couple of forces that we addressed in this in the previous section. A moment that generates a twisting motion without any translation. Okay, so we call it essentially any moment that does not also cause a translation motion we call a couple moment. Again, it's a twisting tendency only. So we'll start with a simple example of how this works. So if I take a look at, I have a beam here that is connected to the wall. This will be the origin of our coordinate system, that's point O. And it extends out and then up. Cut this off so I can draw a force on the top. Okay. We have a couple of forces acting here. We have, right in the middle here, we have 750 newtons acting here along the line of point O. We have 200 newtons. At the top of this section, we have 200 newtons the other direction. And then connected midpoint here, we have a force that extends off like this. This is going to be a 3, 4, 5 right triangle. This has a magnitude of 500 newtons. Okay. So the task here is to reduce this to a single force and single moment applied at point O. Okay. So I'll just leave that alone. I don't have a lot of space here. So again, replace this with a single force and a single moment at point O. We also have some geometry here. This is going to be 1.25 meters. This is 1.25 meters. And that only goes to the middle of this beam. And then from there to there, we have a 1 meter distance. Okay. So essentially, we need to find the force at point O. It's going to have an x and a y component. And we're going to have to find the moment, the resultant moment, the equivalent moment of the entire system. Okay, so let's start with the x components. We'll just start numbering these forces for the sake of simplicity. F2, F3, and F4. Okay, so the force, the equivalent force at point O in the x direction is equal to the sum of all the other forces in the x direction. Okay, we're placing all of the x components of all of these other forces with this one force at point O. Okay, well that equals, well F1 has 0. I'll just do this, I'll write it out. F1x plus F2x plus F3x plus F4x. Okay, F1 has no x component. F2 and F3 have x components. They will cancel each other out, but I'll substitute them in so we can show that. And F4 is going to have something there. So this equals F2x is a negative 200. F3x is a positive 200. F4x is this 500. It's in the positive x direction. So it's 500 times the ratio here. The x is 3/5. Okay. So this equals 200, 200. These cancel. 500 times 3/5 is 300 newtons. So the x component of our replacement force, our equivalent force, is 300 newtons. Okay. We can look at the y. Force at 0 in the y is equal to, again, the summation of forces in the y for the rest of the system, which is F1y plus F2y plus F3y plus F4y. Okay, F2 and F3 are horizontal only, they have no vertical component. So those go to 0. So F1y is equals negative 750, i.e. for 750 newtons downward. Okay, and then F4 has an upward component of 500 times the ratio of 4/5. So this equals 750 plus 4/5 of 500. Negative 750 plus 4/5 of 500. This ends up equaling a negative 350. So that we can draw in here as downward newtons. So what this has essentially done is taken these four forces and said, in terms of the net force moving it side to side and up and down, we can replace this entire system of forces with just one 350 Newton force down and one 300 Newton force to the right. Okay. The reason we do this is eventually we're going to want to know how strong does this support need to be. Okay. This support is it's mounted to the wall. That's the point of this sort of problem. So what this is saying is whatever the support has to do, has to hold, has to be able to take something pulling 300 newtons to the right and 350 newtons downward. So if it can support those two pieces, then it should hold. The one thing we haven't looked at yet though is moment. Okay, so we need to find the resultant moment of this system of forces to see what kind of stuff we can create. Well, see what sort of support we need at point O. So taking a look at moment. Okay. Well, moment, the resultant moment at point O is equal to the moment due to each of the other four forces. It is equal to the moment due to force 1 plus the moment due to force 2 plus the moment due to force 3 plus the moment due to force 4. Okay, so we can go ahead with this. All right, start calculating moment. This is all moment about point O. Again, so it does matter when you start calculating moment where the equivalent force gets placed. Notice when we added up all the forces, it didn't matter where point O was. Again, it's just going to be a net 300 Newton force to the right, 350 Newton force downward. Okay, but when we start dealing about how it's getting twisted, point O's location starts to matter. Okay, so we have moment of force. We'll do moment due to force 1. We'll do these individually first. We'll come back to the addition at the end. Moment due to force 1 is equal to force times the perpendicular distance, the moment arm there. Okay, the force is 750 times the distance, again from point O, perpendicular distance is 1.25 meters. Okay, 750 times 1.25. I don't know off the top of my head. $937.5. That's Newton meters. And that is causing rotation clockwise. So if you wanted to leave that as negative, that's fine, because negative being clockwise. Okay, moment due to force. Oops. Excuse me. Moment due to force 2 is equal to force times its moment arm. Well, that's easy enough. The force is 200 times the moment arm here is 0. So this creates 0 moment. Easy enough. Moment due to force 3 is equal to force 3 times the moment arm for 3. Okay, again, force 3 is 200 newtons. In this case, we have a moment arm. Again, this is moving horizontally, so we care about perpendicular distance of 1 meter. So this is 200 Newton meters. And this is causing rotation clockwise. Okay, so we have 2 clockwise moments in this case. All right, moment for 4 is going to be a little bit tricky. Because it's off pointing at an angle, finding the perpendicular distance is more difficult. What I can do, however, is split this into 2 pieces. So we're going to have F4x, oops, that would be y because it's vertical, and F4x, which is the horizontal component here. Okay, we can find the components and then find their respective moment arms. So I'm going to write these because I'm running out of board space here. Moment due to force 1 is equal to 937.5. I think I'm going to roll with the edge here, but that's fine. Newton meters clockwise. Moment due to force 2 equals 0. Moment due to force 3 is equal to a 200 Newton meter clockwise. So I can take these 3 down and we'll take a look at the last force here. Calculate the moment here about 0.0. So F4 in the x is equal to F4x times its moment arm. Okay, the x component here is 500 times the ratio in the x direction is 3/5. So this whole piece is the force. Okay, force in the x direction. The moment arm here is going to be here to here. Again, this is a horizontal force. We're looking at vertical distance, 1 meter. So 500 times 3/5 times 1 is 300 Newton meters. And this one is also trying to twist it clockwise. Last but not least, we have F4 in the y is equal, oops, this should be moments. Sorry. Moment due to F4 in the x, and the moment due to F4 in the y is equal to F4 in the y times distance equals, okay, this is 500 times 4/5 for the vertical component here, times moment arm, again from here where the force is applied to O, we're looking at horizontal distance for vertical force, is 1 1/4 plus 1 1/4, it's up to 2.5 meters. So this is 500 times 4/5, which is 400 times 2.5. 400 times 2.5 is 1,000 Newton meters. And this one, this 0.0 here, this force pulls upward, is going to cause a counterclockwise rotation. Okay, so the force that I labeled F4, this 500 Newton force, is actually generating 700 Newton meters counterclockwise. We split that into 2 components, one that was going 300 clockwise, the horizontal component, and the vertical component caused 1,000 counterclockwise. We could recombine that and find the total moment due to force 4, but we don't really care about the moment for just force 4. We care about the moment for everything put together. So I'll add everything together. to get the total moment about point O. Is equal to, well, we have 937.5, oops, 937.5 Newton meters. That's clockwise, so we'll make it negative, plus 0 for force 2, minus 200 Newton meters. I haven't put meters in there. 200 Newton meters, because the 200 Newton meter clockwise force for F3, plus what we have for F4. Okay, F4 we had two pieces. We had a negative 300 for the X component, plus 1,000 for the Y component. Okay, so we have three forces that are contributing to the moment. Okay, and one of them we had to split into two components before we could calculate. So we work this out here. This ends up being negative 937 minus 200 minus 300. So it's negative 1437 plus 1,000. It's negative 437.5 Newton meters, or 437.5 Newton meters clockwise. So that means when I replace my equivalent moment here, I have a net 437 Newton meter moment rotating here. I'll draw that in here, 437.5 Newton meters. So essentially when we try and support this beam here, when we try and support this structure against this wall, we have to count for 300 newtons of horizontal force, 350 newtons of downward force, and 437.5 Newton meters trying to twist it. Okay, so whatever this joint or fixture is here has to be able to support that much. Okay, so this was a relatively straightforward problem. The one thing you could have done a little differently, if you had spotted that this 200 to the left and this 200 to the right were a couple, you could have ignored those in terms of force, because they canceled, and just done force times the distance between them, 200 times 1, to get the total moment. And if you notice, F2 and F3 have a total moment of 200, equivalent to 200 times 1, the force times distance there. Again, you can use the couple moment to shorten it up, or you can do it all the way out. It works out the same either way. Okay, so this was a 2D system here. We'll take a quick look at a 3D one to see how much worse that gets. For a 3D system, we'll take a look at a relatively simple one. It's going to tax my drawing skills nonetheless. We have fixed to the ground here, we have a pipe or a beam that goes up. And then it zigs this way. And then off this way. Okay, in terms of coordinate axes, we're going to try and do my best here. This is the origin. We're going to have X in this direction, Y in this direction, Z in this direction. Okay. We're only going to have three forces acting on this. We're going to have a 100 Newton force going directly off the back, the negative Y direction. We're going to have, in the negative Z direction, a 200 Newton force acting at this joint. And at this end point here, a moment that's rotating, and this is going to be, if you look at this, counterclockwise, a moment of 75 Newton meters. And that is a moment around the x-axis. So it is this is moment about the x-axis, so that is going to be clockwise as I've drawn it, so we'll make that negative for a clockwise moment around the x-axis. Okay, as we look at this, again, looking from the positive x, this is rotating this way, that's a clockwise moment, gives you a minus 75 Newton meters. Again, the 75 is given the minus, you have to be able to tell from the direction of the arrow. Okay. So, yeah, I'll leave that alone for now. So, and I want the equivalent force and moment about the orb. All right, well, forces are pretty easy. We're going to have three components. Okay, the nice thing is this moment doesn't generate any force. It's just generating twisting. It's a couple moment. There's something going on there that's causing it to twist. Could be a pair of forces generating a couple. Could just be a torque applied at that point. But it is just a couple moment at that spot. Because it is a couple moment, we can move it around, which we will in a moment. So, yeah, which we will in a second. So we have summation. So the moment, oops, not moment. I'll start with forces. Force applied at point O is equal to the sum of forces L squared. So we'll start in the x direction. Sum of forces in the x. This force does not act in the x. This force does not act in the x. Moment doesn't generate any force. Done. No forces in the x direction. That's all set. Force is about O in the y, is summation of forces in the y, is equal to, okay, we take this force is negative 100 in the y. This force does not act in the y, this moment does not generate anything in the y. So we're left with 100 newtons there. Force about O in the z is equal to summation of forces in z. Okay, again, this one only has a y component. This is negative 200 in z. And then this doesn't generate any moment. So the force is really quite easy. So the force here is equal to negative 100j minus 200k. So that's the force that's required at point O to support this system. Okay. Now, the moment gets quite a bit trickier because now we have moment about three axes. We have moment about x, moment about y, and moment about z. Couple of ways we can do this. We can do R cross F on both forces, get their total moment, and then just add them up. Okay, this one's simple enough. It actually might make more sense to calculate individual moments for each. Okay, so a moment about point O about the, start with the x-axis. Starting with the x-axis. Okay, that's the moment that's causing this to twist this way about the x-axis. So we'll take a look here. This 100 Newton force, okay, does cause rotation about the x-axis. It's causing rotation counterclockwise about the x-axis, if you look at that. So we have, oops, I need to give you geometry here, huh? We have, let's make it 3 meters to there. We're going to have that be 5 meters. Now I'll make these smaller so the numbers keep reasonable. 0.3, 0.5, and that distance is 0.4 meters. Because we are going to need to know some distances here. All right. So this force, we have this fixture here on the x-axis. This thing's going to cause rotation this way. Okay. So we have 100 newtons. I'll leave the units out for now. Times perpendicular distance. Okay, this is where it gets tricky. We have an axis we have an x-axis, and it's the force is being applied in the negative y-axis, so that is perpendicular to each other. The distance between them is this z-axis distance here, that's 0.3. Okay, so we get a force that's acting one direction horizontally around this other axis that's also horizontal. It's the perpendicular distance that's important here. It's confusing because these are both horizontal, but because it's three-dimensional, they can both be horizontal and be perpendicular to each other. So that gives us the moment due to that force. Moment about the x-axis for this force, same idea. We are going to have, and notice that this is counterclockwise about the x-axis, so it does remain positive. This force, this 200 Newton force, is causing a clockwise rotation about the x-axis. Again, if you think about a beam like this, if you tried to pull it this way, it would rotate about the x-axis. So we have, this is going to be minus, because it is going counterclockwise, it is going clockwise now, 200 times the perpendicular distance, again, from the x-axis to where the force is applied is 0.5 meters. Okay. Now we also have this applied moment here, negative 75 Newton meters. It's already, the negative sign's already there for the clockwise arrow. So we'll put a minus 75 there. Okay, so we have 30 minus 100 minus 75, so that's minus 145 Newton meters about the x-axis. Okay, so we will get 3 components for our moment because we are in a 3-dimensional problem. Moment about O around the y-axis. This is actually going to be easier. Okay, this one's actually going to be quite easy. Now we're taking a look at what's going to cause it to rotate about the y-axis. Okay, in this direction, this force is acting along the y-axis. It doesn't cause any moment. This force is acting directly down on the y-axis. So it's also not going to cause, if you want to think about this, if I have my little beam structure here, I care about what's making it rotate like this now. Okay, if I pull down on here, it'll rotate about the x-axis. A minute ago we cared about this rotation. So as I pulled this way, it would cause rotation this way. As I pulled down, it would cause rotation this way. But now we care about whether it's going to rotate about the y-axis like this. Okay, this 100 Newton force this direction does not cause it to rotate this way about the y-axis. Downward here does not cause it to rotate about the y-axis. This becomes very simple. 0 for the first 400 Newton force, 0 for the 200 Newton force. This moment's about the x-axis. No components, nothing contributing to rotating about the y. This thing has no inclination to rotate about the y-axis. Z-axis is, I believe, going to be the same thing. Moment about z. Okay, we could take a look at my beam again here, or my beam made up of markers. Okay, if I have this beam here, and now I care about rotating about the z-axis. That's rotating this way. Okay, again, my force acting this way doesn't cause it to rotate about the z. My force pulling down here also doesn't cause it to rotate about z. These two forces really just made it rotate about the x. There's no rotation about y or z in this problem. So we end up with 0 plus 0 plus 0, 0. And this was my j component, and this was my k component. So the total moment about O, the result moment about O, is just negative 145 Newton meters in the I direction. Okay. So we end up with that sort of system. Now, if this geometry was really confusing for you, if you have trouble envisioning where things are going to be causing to rotate, you can always, always, always do R cross F to calculate each moment, which I'll show will give you the same answer. Okay, for this force, we have force equals 0I, this is the 100 Newton force, 0I minus 100J plus 0K. Nothing acting in the X or Z direction, it's only acting in the Y. R is the distance from O, the position vector from O to where that force is applied. Okay, we don't go anywhere in the X, we don't go anywhere in the Y, we go up 0.3 meters. Okay, so R cross F is going to equal, again, I, J, K. R is 0, 0.3. F is 0 minus 100, 0. Solving this out, we have 0 minus 30 I J, everything drops. K, we have 0 times 100, 0 there. Okay, so for the 100 Newton force, all we get is a 30 Newton meter. So we'll do for the 100 Newton force. We'll do moment equals is negative 30 I, and that's in Newton meters. Okay, we'll do the same thing for the 200 Newton force. F is 0I plus 0J minus 200K. R is, again, nothing in the X. In the Y, it's over 0.5. In the Z, it's up 0.3. All right, so we need to combine these. R cross F. I'm going to do this a little smaller this time. I, J, K. R is 0.5.3. F is 0, 0, negative 200. Determinant of that. I, we have 0.5 times negative 200, 0.3 times 0. We end up with, this is equaling negative 100. That is negative 100 with something is goofed here. Yeah, sorry. Okay. Backing up a second. Taking a look at this determinant, I did this one wrong. My apologies. I, J, K, 0, 0, 0.3, 0, negative 100, 0. J and K are also going to drop, but my mistake was on the I. It's 0 minus a negative 30. So this should be positive. Okay. So we do end up with a positive 30 for the moment about 0.0 caused by the 100 Newton force. So that means this is going to come out, right? Which is good. So we have minus 100I. J, we have 0 times negative 200 times 0.3 times 0 drops out. K, we're going to have 0 times 0. So we're only left with this as well. So these combine to moment about O of negative 100I. Okay, well, we also have this applied moment of 75 Newton meters. The moment due to that, again, it's a couple moment, we can put it anywhere. So we're going to move it from there, we're going to move it straight to 0.0, it's going to stay as negative 75. And it's about the x-axis, so that's I. So when we add these three together, we get 30 plus negative 100 is negative 70, minus 75 is negative 145. So we end up with the same answer either way. If following the geometry and which way things rotate seems easy to you, find the easier way to do it, that certainly works. If that just you have trouble visualizing that, you'd rather just work through the numbers, you can do R cross F for every piece, and it'll get you the same answer as well. Okay, so that is resultant force systems. There's one other case we have to deal with in this section, and that's when your force is not applied in an individual point. That is when we are dealing with something called distributed loading. Okay. Starting with a simple case, we'll take a look at, let me find what I want to do here. Okay, if instead of my beam that has forces all over it pointing in different directions, let's say, let's fix wall here, let's say I took a beam and I said, I'm going to apply a load. I'm going to pile something on top of this, something that's got some weight to it. So I'm going to put something on top of this. This whole section is going to have weight weight applied to it. Okay, that's the way to think about this. Is in reality we talk about, well, in most problems we talk about forces being applied at a single point. Okay, in reality that's still going to be distributed over some distance. Okay, this is the case when I have force applied over a much larger area. Okay, and apparently the board's not all that clean. So we've got this beam here, and we have something piled up on top of it, something causing a force that's distributed over the entire beam. Okay, so I'm going to say this is arbitrarily, say, 10 newtons per meter, and then this is going to be, we'll just say 5 meters long. Okay, so finding the total force on this thing is really quite simple. Okay, you've got 10 newtons for every meter of length, okay, and you've got 5 meters of length, so the total force is equal to 10 newtons per meter times 5 meters is equal to 50 newtons. So there's a total load of 50 newtons downward on this beam. That's easy, okay? If you want to think back to your very big or pre-calculus here, when you started talking about splitting this into tiny little rectangles, okay, each rectangle is going to have its own little force, okay, and that'll become a little bit more relevant when we start looking at stuff that's curved. But we can look at each one of these little slices, and each slice is going to have its own amount of weight applied at its own point. The tricky part here is what happens is when we try and reduce this to a single force, where do we apply that force? Okay, so where we apply the force does matter, because if I want to find the moment about point O, if I replace this whole distributed load by a single force, I have to replace it with a force that generates the same total force and the same total moment. Okay, so for a rectangular piece like this, it's fairly intuitive that you're going to want to put it right in the middle. So my resultant force is right here, 2.5 meters from the end, with a force of 50 newtons. Okay, that makes sense because if you start thinking about moment, each little slice over here is going to generate a tiny amount of moment. Each slice over here, again, force times distance, is going to generate a much larger amount of moment. And those two are going to be balanced with these two here. Again, the amount of moment generated is going to be the same. Not from here and here, but the amount of moment generated across the whole beam will be this equivalent to the moment generated by this 50 Newton force. Easier way to think about this, if instead of calculating moment about point O, what if we calculated moment at about some point A here? Then we look at, all right, the sliver on either side of the distributed load here, those are going to balance. Each sliver as you move outward is going to balance. So the total moment about point A is going to be 0. If we have a 50 Newton force applied right at point A, the total moment is going to be 0. Okay, so by replacing this entire distributed load by a single force, we can look at this point and say, okay, it's going to be balanced whether it's a single force or whether it's the entire distributed load. It's still not going to have any moment about point A. The cool thing is that it doesn't matter if we look at point A or point O, or if I put point B way out here, it's all going to be equivalent. Okay, we replace this distributed load by a single force. Distributed loading that's essentially the approach to distributed loading. We're going to replace a force, replace a distributed load, with single forces, where the force is equal, handwriting problems, equal to the area. And I'm putting area in quotes because when we draw a distributed load. We draw it as a rectangle or a triangle or whatever else, but the units are newtons per meter or meters. It's not truly an area, but we're looking at the area of the geometric shape on our diagram. So equal to the area of the distributed load. And the force is applied through the geometric center of the distributed load. Okay, so in our little rectangle here, got our beam, our distributed load. Okay, our distributed load is this blue rectangle here. We find the area of the blue rectangle. That's going to be the magnitude of the force. The position of the force is going to be acting through the geometric center of the rectangle. So the geometric center of the rectangle, again right here, the force will act right through that and be applied on our beam as so. Okay, so a rectangle is the easiest case. The other geometric shape that's easy to work with is a triangle. So if I have a beam here, and I have a triangular distributed load. Okay, so this will say be 100 newtons here, and this will obviously go to 0 at the end. Newtons per meter at the top. Okay, and then we have a, say this is 2 meters to where it starts, 3 meters in length. Okay, so this piece over here is not part of, there's no loading here, so it really doesn't matter to our problem right away. Because all we're doing is we're simplifying this distributed load into a force and its location. Okay, so the area of this triangle, area of the triangle is 1/2 base times height. Again, I'm using these symbols kind of little poetic license here because this is not, the units don't match up like a regular geometric triangle, but the numbers work. So we have 1/2 times 3 meters times 100 newtons per meter. Okay, we end up with 1/2 times 3 is 1.5 times 100 is 150 newtons. Okay, and meters drop, we end up with a single force of 150 newtons. The question is, where is it applied? Okay, if you remember your geometry, in any triangle, the geometric center is going to be 2/3 of the way from 1/3 away from the long edge on both sides. So if this is from here to here, it's going to be 1/3 of the way over. And if this is alongside 1/3 of the way up, which we don't care as much about, really all we care about is where the center is in this direction, because we want to know where on this beam we apply this force. Okay, so this whole beam is 3 meters, the beam is 5 meters long. The distributed load is over 3 meters worth of this beam. Okay, so with the center of this little triangle is going to be 1 meter from the long edge, 2 meters from the narrow edge there. Again, because it's a triangle, we know this is going to be a distance of 2 meters here, and then 1 meter from the other edge of the triangle. Okay, so we can replace this distributed load, and I can actually redraw my diagram, which is usually the ultimate step in one of these. So I've got my beam, it's 5 meters long, and at a distance of 3 meters from the edge here, I have a 150 Newton force. That's 3 meters from the left edge. So in this case, I've taken a triangular distributed load that's over the last 3 meters of my beam, and I've applied it, and I've simplified it to a single force. Once we have it simplified to a single force, you can treat it as you would any other, generate a force in a moment, generate a net force in a moment off this, and keep going with an equivalent system from there. Okay? The next step in complexity is if we have something where, for instance, it's not a rectangle or a triangle, but it's something, I'm going to do this a little differently and try and make this a little closer to scale. And up here, that's supposed to be a straight line. This will be 250 Newton meters. And we have a distributed load that acts like this. Okay, and I'm going to make it the same 5 meter long. Well, for simplicity, I'll make this 4 meters long. Okay. All right. Now this is technically a trapezoidal shaped distributed load. Okay, but it's not something we can't deal with what we've dealt with what we've seen so far, simply because we can split this into a triangle and a rectangle. Okay, so if I were to draw a line right here, what I end up with is, in this green region I have a rectangle, and in the rest of it I have a triangle. So in this case, I'm not going to simplify this distributed load into one force, I'm going to simplify it into 2 forces, which is fine. We can work with a beam with 2 individual forces on it. That's not so bad. We'll just add them up and calculate the moment at the end. That won't be so bad. Okay, so what I'm going to do is I'm going to simplify this. 4 meters long. Okay, this rectangle is 4 meters by 50 4 meters wide by 50 Newton meters high. A rectangle, area is just base times height. So 4 times 50 is 200. I'll do this, I'll write this out. We have the rectangle. The force is equal to 50 Newton meters times 4 meters, which equals 200 newtons. The question is, where is it? Well, it's a rectangle, so it's going to be right in the middle. We have a 200 Newton force at a distance of 2 meters from the edge. The triangle is a little different. The triangle, okay, that's this region here, this section of my distributed load. Okay, its area is 1/2 base times height, or in this case, the force is the area. The force is equal to the area, which is 1/2 base times height. Okay, so we have 1/2. The base is still 4 meters. I'll do this here. 1/2 times 4 meters. The height, okay, the height, notice it's not the entire 250. The triangle goes from 50 up to 250, so that's a height of 200 Newton meters. Okay, we've already accounted for this stripe across the bottom of 50 Newton meters. Now we're just looking at this top part. Okay, the bottom part was the rectangle. Now we're just talking about this triangular piece, which starts at 250 and goes down to 50. So that's a 200 Newton meter difference. This equals 1/2 times 4 times 200 is 400 newtons. Okay, so we have a 400 Newton force somewhere in here, and it's going to be applied 1/3 of the way from the long side of the triangle, from the tall end of the triangle. Okay, so this is 4. So 1/3 of this is going to be 4/3. So we're going to have a force here, right about here of 400 newtons, and this is going to be 4/3 of a meter, 1.33. And if you want to figure the rest of this out, this distance here is going to be, what does that end up being? 2/3 of 4, so that's going to be 2/3 of 4, 8/3 meters, or if you'd rather, 2 1/3. Okay, whoops. 2 2/3. Doing math, right? All right. So again, we end up with 1/3 of the distance here, 2/3 of the distance there, and we find that we've essentially simplified, not essentially, but we have simplified this distributed load into 2 forces, and we can treat these 2 forces as point forces acting on our beam and find net force and moment. Okay. Now, when we don't have something nice like this, when we have something that can't be simplified into rectangles and triangles, things get a little bit more ugly. Then, to be honest, we have to work with, we have to find an equation for the line or the function applied to our loading. So I'll start with something simple here. And I'll simply go to 1 meter along here. And then I'm going to say there's a distributed load that's shaped like this. And I'll say this line, oops, this line follows the function 1/2 x squared Newton meters. So essentially, this is my x-axis here. As x increases, this distributed load follows this function until we get to 1 meter at the end of the beam. Okay, so when x is 0, obviously there's no loading here, there's nothing there. When x is 1, we have a loading of 1/2 Newton per meter. Okay, so this load is distributed parabolically in this case over the beam. There's no way to separate this into rectangles and triangles geometrically. What we end up with, again, same way we used to find area under functions when you were in calculus, is taking an integral. Okay? So the total area is pretty straightforward, but finding the placement of the moment gets a little bit more tricky. Okay? The magnitude of the force is simply equal to the integral, and I'll say this, I'll give this is typically W. I don't know why they use W for distributed loads, but maybe it's for weight. But they do typically use W for distributed loads, at least in our textbook. So W equals, so this is the integral from one end to the other of W of x dx. Well, and this is integrating over the length of the distributed load. For this case, it's really not hard. We have F equals the integral, again the length goes from 0 to 1. The function here is 1/2 x squared dx. Integrate that, we end up with 1/6 x cubed, and evaluated from 0 to 1, equals 1/6 minus 0. Okay, again 1 cubed is 1 times 1/6, and then 0 cubed is 0 times 1/6 is 0, equals 1/6 of a Newton. Okay, so this is really not a lot of loading. It's 1/6 or 0.167 newtons acting on this beam. But so the force is, I'll do a point, I like working in decimals, 0.167 newtons. All right. That's the easy part. Again, finding the force. Now, finding the moment. If you think back again to when we used to split integrals into little rectangular pieces here, each one of these rectangular pieces generates moment, right? So we end up, when we used to add up all the areas, we got the total force. Okay, well, in this case, to add up the total moment, we have to have all those little areas, those little forces, times their distance from the origin. So to find moment, again, we'll put the origin right here. Okay. The moment about point O is not just the integral of f of w of x, sorry, dx over L, but we need to multiply that by x. Okay, multiplying that by x though gives us a much bigger piece here. We're only really looking at the distance. Okay, we want to know the location. This will give us the total moment, which is wonderful, but to get the position of the moment arm, okay, moment about O is F times D. If we want to know D is moment about O divided by F. So that becomes the integral over L of x times w of x dx divided by the integral over L of w x dx. This is the location of the applied force. Okay, we found the 0.167 newtons. So that's going to make our lives a little easier. One, we know how big the force is, and two, that's actually this piece here, so we can save ourselves a little math. But we're still going to have to evaluate this. Okay, so I'm going to rewrite this and evaluate it to find exactly where this force goes. So again, D equals, I'm going to do the whole thing out here, the integral from 0 to 1 of x times w of x dx over the integral 0 to 1 of wx dx. Okay, the top becomes the integral 0 to 1. X times wx is 1/2 x cubed dx. The bottom is just 0 to 1 1/2 x squared dx. Okay, we've already evaluated this. I'm going to bring this down here. The top piece, we'll do this equals, we know the bottom piece. We did that already. We found the force. 0.167 newtons. We just need to evaluate this top piece. So the integral, from 0 to 1 of 1/2 x cubed dx is equal to 1 over 8 times x to the 4th, 0 to 1, is equal to 1/8 minus 0 is 1/8, or 0.125. Okay, so this goes right up here. Oops, this is Newton meters. Okay, because this is, notice we've taken newtons and multiplied by distance meters. Units aren't terribly important here. We know the answer is going to be meters because we're looking for a distance. 0.125 divided by 0.167, or 1/8 divided by 1/6, is equal to 0.75 meters. Okay, so that ends up being our position here. So we can replace this entire force here. So D is equal to 0.75 meters. So this entire distributed load, we did have to go through a little bit of messy calculus here, but this entire distributed load can be replaced by a single force right here at 0.75 meters from the end, the magnitude of 0.167 newtons. So that entire messy distributed load reduces to a single force and at a single point on our beam. So we will eventually get to the point where we combine distributed loads with point forces, but really that's not any different or difficult than anything else we've done. You simply start by reducing your distributed load to a point force, redraw your diagram with your new point force plus any other point forces you have in your problem, and you go ahead and solve from there, which we'll see in some of the examples in class. And that wraps this one.